So just kind of waiting for people to find their way back. No mast. The app just crashed. It just crashed. Yeah, I don't know. I didn't look at the crash report or anything like that, but macOS is just saying, boom, OPS crashed, and I couldn't start it. I don't know why. I just kept bouncing on the dock and it just wouldn't start. I had to force quit it a couple of times. Do a quick reboot. I don't know. Maybe it's my webcam driver that caused it to crash. Who knows? This stuff is just like super janky, built on duct tape and glue and stuff like that. I mean, it's really cool that OBS is like an open source program and it kind of works. But it's it leaves a lot to desire. Yeah, I think personally, I very highly value reliability in software. I think that's one of the key aspects of quality. That a program does what it is expected to do within the amount of time you expect it to do it, right? So within the bucket now goes everything from latency and stuff, but also just like, a thing just not crashing midstream, and then YouTube just like not making it possible to continue the stream is kind of crazy. And the whole stream just closed down, right? You couldn't talk anymore in it. I couldn't drop in the link to the new stream or anything like that. It's a very bad experience, and I think that is an example of unreliable software, right? Both the streaming software I used as well as the YouTube experience. Anyhow, it's easy to complain, but it also makes it hard to enjoy these things when it's so much work just to make it do what you expect it to do. Anyhow, it looks like, I don't know, it looks like most people just got lost, or maybe it wasn't very interesting. I'm gonna wait a few more minutes, see if people find a way back, and otherwise I think I just won't do this live stream. I will just end it here, and I'll just do a recording instead. But let's give it a few more moments. Hi, Jack. Yeah, they have a little counter here I found. If I scroll down to the bottom of the YouTube page, it says 5 people watching right now. Oh, hey, Jonathan. Congrats again on your item. I don't know if you want to. Hey, Parker. Oh no, I do, yeah, no, I do have a M1 Mac. I have a lot of Macs actually. I have an M1 Mac here, 14-inch Macs. It's really nice hardware, but Mac OS 12 I think is just like so bad. So no, I am still using a 2018. Let's see here, a 2018 15-inch MacBook Pro. It is more than enough for the stuff that I do. I mean, having a discrete GPU makes like all the difference for a computer. It allows me to use Figma and stuff like that really efficiently and do graphics programming and stuff like that. So no, this is great. M1 unfortunately requires macOS 12, which I am not interested in running. Appreciate the computer hoard. Yeah, well, I try to not hoard them too much and sort of give old ones away. But there's a whole bunch of stuff behind me here. But yeah, there's a couple of ones up there, a bunch of keyboards and stuff. There's a couple of computers outside of the screen here too. But anyhow, we're not here to talk about computers. Elementary OS. Yeah, I do have one of my computers outside of the screen here. I have 2 PCs. One of them has Ubuntu on a partition. Sorry, it used to have Ubuntu. It has Elementary now, and yeah, no, Elementary is a really nice Linux distro. Okay. It looks like there are a couple of people found their way back, and I'm just gonna go for it. And I think unless OBD breaks down again, which who knows, or OBS, is that what it's called? Yeah, I think it crashed again actually. I don't know. Oh no, I think my web camera crashed. Can I shake? Let's see. I think it was quick enough to get it restarted this time. Um, and it looks like, looking at the YouTube, it looks like it's up and running. Yeah, I think my guess here is that there's an issue with the camera driver that I'm using for my Fuji X Pro camera, which is the one that had the nice picture. And so I'm just gonna sort of shut that off. I disconnected it, and now OBS started up again before it was just kind of taking forever. Sorry, this became like a video about how complicated it is to do videos. Anyhow, I hope this will work. I'm just using my crappy little built-in camera into my display. At least you have a little face in the corner. I can just do that. Okay. It's amazing. I think it's working. Okay, lovely. Getting back to this. In the chat, you can, if you joined and didn't get the first part or whatnot and don't want to rewatch it, just let me know in the chat and I can do a quick recap of where we are. But otherwise, I'm gonna assume you were following along before. So we're looking at the way to evaluate the virtual machine program, and we're looking at the three different strategies: a big switch statement, sort of a address jump table, and a tail call function table. And now we're sort of like trying to figure out like which one will give the most ergonomic experience for writing this program that's short and concise, that allows us to play around with instructions and stuff like that, and pros and cons of that. And we can also look at the code that generates just to sort of like get a better sense of what the technical trade-offs are for these different approaches. So maybe we should just start there. So a switch case, this is the current strategy. We have that running on the site. If we have a look at, I have put together a little script here. Let's see, there it is, and we can just open it up. You can see what it does. So we run the script. It just goes and just compiles this one file, the eval file here, to just assembly for x86. And then it just removes some decorations in the assembly output the client generates, but no actual like data or instructions. And then we just look at it and I count the lines at the bottom here. Okay. I also have that file open here so we can switch to it and have a look. So this first strategy, then we have this one function. There's just one function in the strategy, and none of this is being used, right? So this is not there essentially. Then we have this state for a loop. So exec here is like a label that next here will jump back to exec, and that increases the, it grabs the next instruction from the array of instructions, increases the program counter, and just grabs the first argument because all of these are gonna need it. And then it just jumps to one of these, right? And then it repeats. So there's a loop going on until it hits ret. The ret instruction, in which case this eval function just returns. Okay. So what's going on is we're gonna look at this RSM eval function. So we're gonna scroll up here. And this is actually a relatively small code. Now all of these dlog statements are just excluded from this build. Otherwise there would be a lot of stuff here. So this x86, so this just sets up the stack for this function, and then we are doing, let's see, where is that? Yep. So this bit shift right is what's happening in here. This macro, if we jump over to these guys here, you're gonna see bit shift right. So that's what we got, and we're gonna have an AND. So that's the AND operation here, and the mask, it just, the compiler just figured out that that's 31. So there's nothing else there. So we have two operations happening. That's where they come from. Sorry, eval file. And the next thing it does, so now this is interesting. So when you use a switch statement, right, you have something like, switch, like a thing, right? And now we have a bunch of cases. So case, 1, do this. Case 2, 3, 4, do this and do that. It's sort of like a fork in the road, right? You walk out in the woods, and suddenly the road splits in 3 ways, and you have to choose which way to go. That's kind of like a switch statement in a nutshell, right? So it can be really useful for a lot of things. It's a really ergonomic construct, I think. Many programming languages offer them. Some, with discriminated unions and stuff like that is kind of neat. We just in this case like really basic with just numeric constants, as in C. What's neat about it though is that it is a high-level construct, and the compiler will do really clever stuff, like trademark at the end. If you have a like maybe 2 or 3 cases, and the code is kind of small, ish for each of these cases, it's probably just going to do comparison things, like equivalent to if you use if, else if, else if. And if you have a lot of case statements or a lot of code in these case statements, it might. And this is what it's done here for us. We're using Clang. Let's produce this. What it's done now is actually implementing a jump table for us, which is the second strategy we looked at. So what this means, load effective address, this instruction. So this just goes and grabs it loads the offset for the jump table that it made for us, and it gave it this like kind of, if you look at just this, it's kind of fun. It's like a face. But it produced this jump table and gave it this kind of Yankee name, and we gonna find it at the end. Oh, I think I kind of accidentally stripped that out. Luckily, I did save. Oh, I did save the unstripped version here. Okay, so long. Okay, not a quad. So yeah, here it had generated a table. So this is a table. It starts off at 0. And there's gonna be a long, it's gonna 8 bytes on this, so byte 8, and we can have 16 here, right, and so on. And then these ones are labels, and these are constants. That this is assembly. Again, this is not machine code, right? So the assembler will chunk these into the the read only. It depends, ELF or Mecca or whatever. It'll chunk these things into just data. Read-only data into an executable if you were to build an executable here, and it will, and these are gonna do the same thing essentially. So what it does is for this, for example, which is down here, this is an address of an instruction, and it does this fancy thing. LBB06 is a auto-generated name for a label that is up here, and this is going to be, this is easier, we can just look at this. So LBB03 corresponds to this condition here, and 04 to this, and 05 and so on, right? So jumping back to the code, I'm going to stop here and we can look at the right side instead. Now we know my little grep macro here, grep thing is to erase those constants, unfortunately, but everything else is there. So it did generate a jump table for us. It's kind of interesting. And GCC will do the same thing. You can use things like godbolt.org and stuff to explore these things if you don't want to do it like this in the terminal. Okay, so at the end, so what it does here is just loading the address of that table, of the jump table, into register 8. And the next thing that it does, so we can follow along up here, right? It increments the program counter. I'm pretty sure that's what it does. I should, and I'm pretty rusty at x86. I haven't written it in a long time, but let's just skip past that. I don't know. I might be lying, and I don't want to say something that I'm not confident about. The next thing it does is just oh shoot, oh yeah, it will be the it will be this thing. This thing does. So it would essentially load the operation. That's what it's doing here. Okay, it's the AR has the operation, and then it now has an offset, so that's why it's adding this Okay, obviously that's what it's. It wasn't obvious to me for a second, so I shouldn't say that. But in the yump table, um, it added on the value in register C here, or CX, which would be the where we have loaded the current opcode. Right. So up here, we've done get up, and they get loaded into register CX, and then it adds that on to the offset of the yump table, and now you got the address in the yump table. I think that's what's going on. And then just does yump. Now x86, it's an legacy laden instruction set. There's 10,000 pages of manuals and stuff you can read about it. So some of these have a little quirky things, like Q is like a quad. It's like you have a different letter here. It's just the size of the argument. So that's why I'm saying is jump and not jump Q. Okay, so jump here. This now will move if we imagine that the program does this, down like this, right? Comes to this jump instruction. Now what it's going to do is like not just go here. It might, but it's probably not going to do that. So it will jump to whatever executable address is loaded from register CX. This little asterisk means to load the value from it. So that's the jump that we're doing, right? So if we now found an operation called BRZ, right? Then what's happening here is that we'll do a jump past all those things down to BRZ. So now if we go down here, and then whoop, it might jump down here, right? If this is BRZ, and now it will do a thing. So this is the actual code, or an example of the actual code that one of our virtual instructions would equate to, right? This is what the virtual machine would translate over to x86 in this case, or some other architecture like ARM. And when it's done, in this case, it's just, we can see it's very efficient. The only overhead here for having an extra instruction operation here is really just this jump at the end. Is essentially zero overhead in this case, which is very neat, right? So it does the thing it does. In this case, we just fill these with just some assignments to this register set. We just do this to make sure that the compiler doesn't eliminate this code, so we can look at it. So the move L we see here, which is a move like a copy this to that. That's essentially what's happening, right? We copy this value to this location. And then it does what it does next, right? Is kind of interesting. So now it jumps back here, which I think if we look at this, yeah. So it's interesting. So the compiler has now generated roughly the same code twice, but it's skipping this load effective address instruction. But otherwise, it does something very similar. We can see the add Q here being reflected here, right? The same thing. And it is setting something to 2. Yeah, let's skip that. And then it's jumping again. And now it jumps to another thing. It does another instruction, and then jumps back. And here, what all of this code does, it's the same stuff that we just walked through up here. It's just, again, the compiler has decided that it's got to be more effective to duplicate this code, which I'm not sure is true, but that's what it decided to do. So it does the same thing. It increments our program counter after it's loaded the next instruction, and then it does shift and an and to extract the value of the argument A. Again, you can look up this here if you're curious what that means. And then it does it looks up the operation of the instruction. So this macro corresponds to this thing, right? And then it does a load from the table, and now we're at this point here. It loads from a table. It adds the operation, right? And then it jumps to the next level. So really efficient. Okay. So it's kind of cool. We've seen here that if you just write a switch statement in many cases the compiler will just be really smart, and modern compilers are just like just mind-blowingly good, or smart maybe is a stretch, but mind-blowingly good at generating really efficient code. So it's almost like the higher level constructs you use, the better code you're gonna get. Uh, it's could feel exciting or enticing to try to do what we're going to try to do next, right? To implement this ourselves, and we're going to see that we're probably going to get worse code of at least the same code. Okay, so let's switch to strategy 2. With strategy 2, and I'm gonna X this out just to what's going on? There we go. Just to show you that it works, right? Okay. So strategy 2. Now the corresponding macros here are going to change. Now we're going to, instead of having this high level switch, we're now going to explicitly load the address of an instruction. I'm going to build a table. So we generate that with a preprocessor macro down here. This thing, I mentioned this earlier, this is sort of like a quirky little way to just grab the address, the effective address of a label. This is something that the compiler will do for you. It's a bit tricky since you have a chicken and an egg, like, where's the address of it? You don't know until you actually like assemble everything into machine code. So that's how we can build a table here. I'm not sure. I don't think this is C11, but I think it is some sort of extension that's been supported by Clang and most high-end C compilers for a long time. In GCC for sure. Most of these weird things are GCC inventions, so I'm guessing that's what it is. So we're building a load table. Instead of doing switch, we just go to a specific address, and then instead of doing a case sort of a case thing, we just enter a label. So that's in C again. How you will tell the compiler that like whatever follows this, whatever instruction follows this label in the code that you generate, give it this name, right? So that I can reference that in other places with go-tos and stuff. And the rest of it is unchanged. There's nothing else that differs. It's only the way by which we dispatch the next, or route rather, the work we're gonna do, right? So we're doing different work for different instructions. So we see that it works the same way when we run this. And if we run this thing now again, that just compiles it to assembly, and we inspect the assembly, we're going to see that we're actually getting worse code. And I think what is happening actually is by pattern recognition. I think it is doing some inlining perhaps, but that doesn't really matter what it's doing. We're just getting a lot more code. If this actually runs faster, so this is why earlier I was saying we're not concerned about performance. At least I'm not concerned about performance. Maybe I will never be with RSM, and definitely absolutely not at this stage. Like, this is not how you get something to run really fast and efficiently. It's not by like trying to figure out like which instructions it generates before you even put it to good use. So that's not at all what we're doing here. This might very well be much faster than the other thing. It doesn't really matter. What I wanted to show you here is that there is an intimate connection between the way like we structure programs, right, and what code is actually generated from this high level C, right? So in this case, we're like, well, we have to do extra work, right? We have to like generate this table. We have to use this possibly extension that's not standard, right, to make this work, right? And what is the upside? Is the code better? No, it's just like more code, right? It works just as well. It's not like we can do anything new. So that doesn't seem to give us anything over the switch statement. Now, with some compilers, it's not true for the big modern ones anymore, but for some compilers, like one big switch statement is a challenge for things like register allocation. Like you have, a limited number of registers in x86, you have just a couple of them. On ARM64, you have a lot of them. On some systems like x86, now 32 bits x86, you have just a couple, was it 4 or 5 or something like that? Anyhow, so and most compilers, what they will do is like they will do register allocation per function, a function basis, function per function basis. And so if you have a bunch of little small functions here and there, it can, just, and then you just have a few locals, a few variables, right? And let's say that those are, the same or fewer numbers than the number of registers. Register allocation is pretty straightforward. You just hand them out and you get, right? A good register allocator will be able to make really good use of that, even if you have more variables than registers. Anyhow, that is a huge, big topic, very interesting if you want to go read about register allocation. The gist of it is, with one big switch statement, you're going to have all of this code, and some compilers will struggle to do efficient register allocation for that, and your compile times are higher, and your code quality is lower, and stuff like that. Now, I don't, at least from my explorations and my experience with Clang, that's not true in this case. So for us, a switch statement so far seems like a really good option. Okay, so the third one is to use tail calls. So I already talked a little bit earlier about what tail calls. I keep looking at my other camera. That's if I'm looking at it over here. Yeah, I forget. You guys over there. Yeah, macros for the win, Edward. In an earlier part, I was briefly mentioning that I am not shy with macros. I think when macros can improve like readability and the understandability of code, I think it's fantastic. But it's a really thin line to balance there between obfuscating something and making something clear, right? So like next here as a macro, like what does this do, right? If you didn't write this code and you see next here, you have to go look that up, right, to understand what this line of code does. So there's definitely a cost to it, but sometimes it's pretty neat. I think macros in particular for stuff that we're doing right now, experimenting and figuring things out, can be a really helpful tool to just like get stuff done, just to explore things, right? So if I weren't using macros here, right, I would have had to sprinkle these if statements, preprocessor if statements throughout the code down here, and it would be much harder for us to read this and see that that these things are actually the same. Anyhow, so the third strategy here with tail calls. Now I think I already saved this, so we already got a sneak peek of the code it generates, and surprise, surprise, it generates really surprisingly good code. Again, now we're looking at assembly. This is not actually machine code. There might be some final optimizations down here, like push queue, for example. Like let's see here if I remember it correctly. So push queue will increment the stack pointer by the register size, right? So Q 8 bytes. So what it does is that it takes the value you give it, it stores it into memory at the current address of the stack pointer register. So this essentially is like, it's an x86 thing. Some other architectures have a push thing too, but really it's like a bundle of instructions. So it does a couple of things. But it does it more efficiently like this. It's an actual, instruction, not an assembly construct. So it can be a little bit more effective than doing like 3 or 4 instructions that would accomplish the same goal. So that's something to notice here, because each of these functions, so now instead of having switch cases, right, we're dealing with functions. So one function per opcode. What's nice about this from an ergonomic perspective is that we now have these little these little functions that are easy. We can just kind of, we can move them around, right? I'm just trying to get into the move state. We can move them around. The order here is not important. I guess it's not for the switch case either. We can sort of deal with these in the same ways that you will deal with functions. We can take the address of the function in a standard way that is not non-standard. Now I'm keep making assumptions this is non-standard. If someone knows if double ampersand to take the address of a label is a standard or it's not, drop that into the chat. It would be interesting to know. I'm just assuming that it's not standard. Anyhow, so we can do that in standard way, take the address of a function. And the tail call part here is important. So there's a couple of things that that needs to be true for a tail call to be guaranteed in a compiler like Clang and GCC. The number of arguments and the type of the arguments between the thing doing a tail call and the thing it is calling to must be exactly the same. So for that reason, this is not entirely true. Like so this is for the guarantee for things to be a tail call to be true. Then in practice, the optimizing part of these compilers will, like, even if you give it just a few arguments, it will do a tail call for you, or optimize things to a tail call as far as it can, unless there's any undefined behavior or anything like that. But to get a guarantee for a tail call, this has to be true. The arguments has to be the same for the caller and the callee. So for that reason, I'm setting this up that there are, and this is inspired by evaluator, maybe, that does this, or maybe it's just straight up there, I can't remember. But again, the power of macros here, right? So define the parameters, and this makes it just saves me from typing out this on every place where it says params. So every handler function, right, takes these parameters, and then when it calls to the next handler function, these are the arguments, and he has kind of typed those out next to each other, since if we add an argument here or change the name to it, it's much less likely that I'll screw up and forget one about it. Okay. The next call here. So up here, our next thing we do a go to get up to this label, right? That did the next that extracted the next instruction, increase the parent counter. In this version, sorry for the scrolling. In this version, next is a function call, just like all the other things. So it's all function calls, and calls to this function, which does the same thing. So it extracts the next instruction from our list of instructions. It increases the program counter, and then it just jumps into this table, right, based on the opcode. And this table has been generated down here. This code looks almost identical to our label jump code. And this is the entry function, right? So we had one up here. It's just a single function with a loop in it. Down here instead, we have a function that is the starting point, and then it passes the torch on, so to speak, right? It's like, okay, now you go, right? And now you go. And so at this point, where we do eval next, this code runs, right? We do what we just talked about, and it jumps to the next function. So it jumps to one of these functions. If we look at the assembly that Clang spit out for us here, scroll up a little bit, we have the entry function on here. So this just sets things up. This does the same stuff we talked about before. It loads, the offset of this table. We don't have to talk about that. And then it just does a jump to eval next, right? So this is where we begin our little journey. And in this case, I think it added it to the end. It just, it just moves code around, it tries to be clever about that. That's what it did, added it to the end. And so eval next so here's where we start seeing some of the potential downsides in code quality between tail calls and using a switch statement. So it, for some reason, pushes the stack base pointer onto the stack, and then it copies the base pointer to the stack pointer, and essentially it does like stack work, but it doesn't actually use the stack. This function, right? So none of these functions use a stack. So it's just like this. This is just busy work. It's not accomplishing anything. So the compiler kind of failed there, unless I'm like totally missing something. But I don't think this is using the stack at all. So anyhow, it takes the hit of doing that work that it doesn't need to do, and then it does the work of loading the instruction, increasing the program counter, and loading the address, getting the op, loading the address, and into it choose this register AX, and then it does a jump to whichever function matches that, right? So in our little example program, let's see if we can scroll up to one of the printouts. We first have a move And then after that, we got a load, and then we got a BRC, and so on, right? So the first thing it's going to do is going to jump to here, right? So it'll start executing code here. And here again, we see it again does work to save the stack state, essentially. And it does the balancing work down here to restore the stack state, even though it does not use the stack. So maybe there's a way to say tell the compiler, I guess then to tell the compiler, as you finish my thought, to tell the compiler not to bother with those stack things, or rather to say like, hey, this function is never used anywhere else than here. But I think static should accomplish that. That it's just local to this file, this compilation unit. And the rest of the code in here is like pretty straightforward. It's just what we're seeing here. So it gets the argument A, and it loads another register. So the move thing is essentially just copying the value in one register to another register. And then it jumps and it keeps going. So this is a totally valid and viable solution for us, this tail call approach. It will have roughly the same runtime characteristics. It will have the same limitations, which are none, since it does not use the stack, right? It can just keep it won't sort of grow the stack or anything like that, even if it might appear to, right? Since it's doing a call and call and call and call. But unfortunately, the ergonomics here and the code repetition, I think, just kind of erases some of the usefulness of this. At least with this such a good compiler like Clang that is able to produce really good code with efficient register usage for the switch case. So I think the switch case it is portable. It seems to generate good code in this case, and if it ever becomes a performance issue, we can always do one of the other two approaches for that to improve performance. But again, performance is not a question right now. Okay, so what I'm gonna do is I'm gonna make a, let's see, I'm just gonna make a copy of this. I just want to keep this around. So I have a little I just pasted in a temporary buffer. So I tend to keep little copies around of things that are written, so I can go and reference them again later. But now we're just gonna remove all of this stuff and use the switch, right? So this, bye-bye. I'm gonna check in on the stream and see if it still works. Yeah, it does. Amazing. And almost no one is watching. That's amazing. Yeah, this I can see how this is boring to most. Okay, so we can just drop this. We can just inline these things. We can actually just keep these. Put the switch here. Next, short and concise. The case might be just simpler to use the case here. Case R up. Okay. And then this, we don't use this anymore. And all of this goes away. Okay, now 30, 40-ish lines. It's pretty good. I mean, it doesn't really do much. And another thing we can do here, we can just drop this label. We can do a for loop. And before doing this, just to verify that this doesn't have a weird impact on code quality, but I don't think it would. Let's do this. Should never be able to get outside of it. So that's guaranteed at this point. And we can return from our function, and next can become break. Let's see, get these copies of next to. Okay. See if that works. Yeah, that's roughly the same code. LBP1, let's see, jump to 14. 15. I see. Interesting. Let's look at that. I'm mostly curious here. I don't think it's gonna have a big difference. So here we'll just pick up 4. This jumps to 2. Ah, interesting. Yeah, we definitely get more code in this case, and different code too. You know, so the again, I keep talking about perf, but I think it's just important to keep mentioning that this is not about performance. It's more about the quality of things. It just feels good. You know, if you're like making, I mean, this hobby project is not for any commercial purposes, right? Like, so the incentives here are not efficiency in terms of money or shipping things or anything like that. Here, my incentives are like about making something that is nice, you know, that is kind of elegant, that feels good. And so that is the driving motivator by me, is like doing all this work right now. I just wanted to feel good, you know. It's like if you make a nice wooden table or something like that, then you, for yourself, you might take just the time you need to make sure that the wood and yes, it's the right piece of wood, and you know, the way you fold your wood and stuff. It's like all the little things that commercially might not make any sense to do, you would do, right? Or your home, you know, little things that makes things nice. So I think it really doesn't matter what we're doing here. This label is also shorter than the for loop-ish. I mean, this just is good. Let's see, 59 lines. Stick to this. This will be good. More familiar to someone else who might stumble up on this code in the future, or more likely, you know, me. To see that, yeah, break is a familiar thing. Capital letters next is not. It's just less. Issues. Okay, I think we're gonna stop it there. This has been pretty long already. What we've done, and let me exit out of this and run the program again. So what we've done now, we've put together a the beginning, the sapling of the evaluator of the virtual machine. It seems to be working. We know that the code we're generating is nice and small and reliable. We've done it in a standard way, portable way. So if we toss this into another compiler, we can be fairly confident that it'll work and behave in the same way. The code is very readable. It's very straightforward code. We so far, we might add to these locals that we're using here, but so far, like we're getting by with fairly small and clear code. We just deal with a single function. It's all good. So in the next part, we will be fleshing out the other instructions that we need to complete our function, our example function here, and then we will see that running. So here we're calling it. So we'll see that function running, and we'll hopefully see the correct result coming out at the end. And then we would have implemented and completed the first big milestone of this project, which would be to have a full pipeline where we construct a program, we evaluate that program into the actual results. So that'll be a complete, very small, very limited, but still complete and valid little virtual machine. So check out the next part, and I hope you enjoy this one.